Today's topic is this paper that has a cool name that I think is a little bit misleading, but the Infini-attention model. And I know that there was speculation whether or not Gemini uses this technique for the really long context they support. But as far as I know, it still hasn't been leaked how they actually support the super long context. So
Is this the paper by a couple of guys at Google?
it is people like Google. Um,
Yeah, I think
but
I read this. I had
but
the same question in my mind, Ted.
yeah. So, and of course now people are no longer being so open, so we don't know. But so this is an interesting paper. The full title is Leave No Context Behind: Efficient Infinite Context Transformers with Infini-attention. I can assure you this technique, even if it works well, is not infinite. Um, but you know, it's going to be a lot longer than if you just do vanilla attention type stuff. So kudos to them for the self-promotion, right? Um, so the technique is very interesting. I will say, I don't think this is the absolute most well-written paper, um, in the sense that there's some parts that are just a little hard to read, and then there's parts where they leave out details. So they reference something and then they don't just like really clearly say, this is how it works. So I actually had to do a fair amount of like sort of rereading and digging and trying to figure out what exactly is going on. I think there's some code. I don't remember if they had code or if other people have implemented it, but so that would probably clear up any questions. So feel free to ask questions if um, well, as usual, ask questions, but in particular, there's some things that I think are just um, open questions, and I may or may not be able to give my best guess as to how it works. So at a high level, before we get into the details of this paper, what seems to have been done here is it combined the ideas from three papers, from three concepts. So one of them is there was this transformer XL model, and basically what they did is they divided the text into segments and they processed two segments at a time. One segment was sort of a normal window of things, and the other is just like this history thing. And we'll talk about that. And so what happened is the history allowed you to see stuff that was outside of your window, and kind of like a CNN that has like a filter of three, like as you move up the layers of the transformer, as you move deeper in a CNN, basically your receptive field gets wider and wider. And that was the idea, was that your history would get wider and wider as you go. There's this fast weight memory paper, and it was co-authored by the primary author Munkdalai of this paper. So it looks like basically he took his fast weight memory from an earlier paper and incorporated into this transformer XL related concept. And what that does is it creates an associative memory using matrix multiplication. It's something that's very fast, and basically what you can do is you can um, present it with some key, and it'll basically pull out something if it matches that key. That's the general gist of it. Okay.
Is this, Ted, is it a GPU based associative memory, or is it CPU based, or?
It's actually just a matrix in which you store information.
Oh,
So
okay.
yes, it's very amenable to a GPU because it's just a square matrix that you shove stuff in, and it could be rectangular, but you shove stuff in the columns and you retrieve it by the keys in the rows,
Okay.
and voila.
Okay. But it's just a brute force array thing. It's not,
Yeah, it literally is nothing more than just a
no sophisticated
square matrix, but
associative
it's the
memory
technique you
subtrees.
use That's a little
Okay.
bit more sophisticated thing. Okay. And then
Okay.
the third paper is there was this linear attention, which it's referenced, and I see the motifs from it, but it doesn't look like it's actually very explicitly used in this paper. Okay. But this was one of those many papers that said, oh, attention's quadratic. Let's build something that's less expensive, right? So there were the ones that were using like sparsity, and doing like, sparse matrices, matrix factorization. And then there were the ones that were doing different attention calculations. And so this one was doing sort of an RNN style thing that was linear in time. Um, and so the the gist is each of these three papers tried to do language modeling. They tried to say, what if I just put in a whole bunch of text? Does it work as well as a regular transformer? And they all failed. They all were like noticeably worse performance than a regular transformer. Um, and so this is sort of like, okay, what if I combine all three of these together? Can I get closer to the same performance as a full transformer without paying this heavy quadratic cost? Okay. So in this model, what they do is they do have this fast weight memory, which serves as a history for all of the tokens that came a long time ago that you're no longer doing full attention on. Okay. And you have to pre-decide how big you want that memory to be. But once you've done that, the memory is a fixed parameter count. It doesn't scale per se. I mean, theoretically, you might want a bigger memory, longer context, but officially, it doesn't scale with context size. So its parameter count is constant. And then the processing cost for all this is linear with respect to the input length. So it's not even log linear, it's just linear in the number of tokens you pass in. Because basically what it's going to do, it's going to do like one memory access no matter how far you get down. So you could be 10,000 tokens in, and it's going to look at the most recent tokens plus memory. And if you are a million tokens in, it's going to look at the most recent tokens plus one memory. That's basically the way these things work. So that's the super high level overview before we get into the details.
Quick question, Ted.
Yeah.
So the fast weight memory then, is it kind of a first in, first out type of memory, or does it have any?
No, it's associative. So basically, if you think about a Python dictionary, if you put something in with the key um, dog, and then you put something in with the key cat, then if you try to pull something out and you pass in cat, what you should get back is approximately the values that you subbed in when you stored it with cat.
But it's a
Okay.
fixed size. So when, to use your analogy, the Python dictionary reaches the maximum size, something happens.
Yeah. Yeah. And so we'll get into the exact
Okay.
technique, but
Okay.
basically, at high level, I think there's two things that uh that they're hoping are going to happen. So one is you're actually in transformers, you have queries and keys.
Mhm.
So you're actually going to be using the keys to store the values, okay?
Mhm.
And the hope is that similar words are going to have similar keys. And so if you previously stored something for the word great, and now you have the word excellent, that maybe it's not in the memory, but it's close enough that you'll get a match.
Mm.
Okay. The
Okay.
other thing is that it actually is like the way attention works in the sense that you're not going to get back like one discrete thing. You're always going to get back some blended version of whatever is in the memory, right? And so literally if your matrix is 16,000 and by the time you're trying to throw 17,000 things in there, the hope is that it would sort of like degrade softly as
Gotcha.
opposed to a hard either I can't store this or I can't read this
Gotcha.
kind of a
Okay.
thing, right? So, but we'll see
And
the
that's the
technique.
compressive part.
And yeah, that's why they claim it's compressive, is because if similar words have similar keys and similar keys have similar values, then you could imagine you don't really need to store every key discretely the way you would in a Python dictionary, where you're
Gotcha.
like,
Yeah.
no, the word cat and the word car differ in one letter, but the values might be utterly different. So you can't leverage any math. You just need to like allocate storage space for each one, right?
Mm.
So the idea here is, I think, again, none of this is very explicitly laid out in the paper,
Okay.
but that's my interpretation. So hopefully this gives you just like a good high level mental model for how are we going to get out of this box. Is we're going to do attention on a little bit, and then we're going to use the memory to, in a perfect world, tell us, hey, what keys would I have cared about if I had actually done attention on all million tokens, right? And if the memory works perfectly, then like you don't actually need those other 900,000 tokens. You could just say, tell me the ones that I would have wanted anyway.
Hey, stupid question. Like the word great could mean different things depending on the context it's used. And then so is there going to be a problem with that association?
So in higher layers of an LLM, the key, sorry, not the key, the actual embedding for the word great would tend to be context dependent and no longer just based on the word great. So you're right, in layer one, you can't tell the difference between whatever large and fantastic and whatever other meanings of great, you know what I mean? But by the time you get to layer 12, we would expect that great being used in a sentence meaning great grandfather would have a very different vector than great meaning like it was a great party.
Okay, gotcha. All right, thanks.
Okay, so let's drill into these techniques.
Real quick, wouldn't you get that at just one layer? In other words, once you go up one level through a transformer, you should have a contextualized embedding right there, right? I mean, as long as you're...
Yeah, by the time you get to layer 2, it'll be modified. It's no guarantee, though, that great grandfather will have been that much modified, that different from great party, right? But you would hope that when you're like way deeper, for sure, it should have enough context that it should have been modified.
Ted, does that same rule apply to words like it and he and they and stuff like that?
Oh yeah,
Okay.
absolutely.
So they get mapped to...
If you use something like a BERT model, if you use Roberta, then you at the top end, people don't always use them, but at the top end, you get an embedding for every word, for every token, and you can try different sentences like great grandfather and great party and great wall of China, and you'll see that they're very different vectors
Cool.
that you get in the token position of great.
That makes sense. I just hadn't...
Yeah, and that's the whole point, starting with Elmo, okay? Because we had word2vec, and that was like light years ahead of just sort of, all the old-fashioned NLTK stuff, But now, instead of once starting with Elmo, now the word great actually is different depending on the words around it, as opposed to just having to have an averaged meaning of riverbank and money bank,
Right. Thanks.
Okay, so the first of these three is the Transformer XL. And so if you look on the left, this is standard attention, okay? So once you get farther into your text, so what I'm showing here is a diagram of the queries starting from the beginning of your input string to the end and your keys, okay? And so queries always get compared to all the keys for themselves and all the keys that came before. So if this is the 0, 1, 2, 3, 4th query, it's going to compare to itself and the 0 through 3rd, all the keys that came before it. Okay, so if you said, the boy threw the ball, whatever, then ball is going to attend to the boy through and itself and decide what to do. So this is a standard diagram you see. That's the attention mask. Okay. Now, as you get farther and farther in standard attention, what you do is you attend on every key that ever came before you, going all the way back to the very first key in your sentence. So if you're 1,000,000 tokens into Encyclopedia Britannica, you need to calculate attention between the most recent word and all 1,000,000 tokens that came before it. Okay. So ultimately, this pattern looks like the upper, whatever, left triangle part of a square. So it's half of quadratic, right? So the simple thing you can do in order to limit this quadratic cost is you just pick a window. Now this window is way too small for realistic use. It's meant for the diagram. But this is a window of 4. So you can imagine this window is actually, 4,000, something, a little bit more useful in language. And you say like, oh, most of the time, I'm referring to things that appear in the previous words in my sentence, in the previous sentence in my paragraph, in the previous paragraphs in this page, and maybe even the previous paragraphs in this chapter. 8,000 tokens, 98% of the time will suffice. Unfortunately, there's just the times when it doesn't, when now you're talking about chapter 10, which is the beginning of the second half of the book, and it's going to refer all the way back to chapter 1. And now you're in big trouble because you don't have chapter 1 in your window anymore. But this does reduce your cost dramatically. It's wonderful. Okay, so it guarantees that at most you're gonna compare each query with n, where whatever your window size is, in this case 4 keys. Okay, so what Transformer Excel does is they say we're going to use windows, but we're going to have 2 of them. We're going to have this normal one, and we are going to do regular attention inside of this window. So again, this is a very tiny diagram for the purpose of fitting on the page. So we're only going to do attention on these 4 keys. But I'm also going to do this special thing where I pull out the previous 4 keys. I'm going to have a second window there. I'm not going to do normal things with this. I'm going to do something slightly different with this. Okay. And if you're sort of moving from left to right, you can kind of cache this information. So it's kind of lying around. So what exactly do they do with this second window? Let's see here. Basically, if you think about the way queries are dotted with keys, you do this matrix multiply. Okay, and it's normally a square matrix. Okay, but what they did in Transformer Excel is they had separate parameters for when the query is being compared to one of the green keys. Okay, than the normal parameters that it's using when it's being compared to one of the blue keys from this previous diagram. Okay, and the reason for this is because they don't want the green ones to act just like position n-4, n-5, n-6, n-7. They want these to act more as like rolling history. All right. And so they're saying we're going to treat this a little bit differently. And one of the things that we might do, I believe, conceptually, is we'll say, even though I don't super want to attend to one of these tokens, I'm going to attend to it a little bit in a special way so that I can just save it and pass it along. So the information just isn't lost. So imagine like an RNN, right? Where you have your input and you have your state, and you might say, like, simplistically, I'm going to do something like, 0.8 times my state plus 0.2 times my input, right? I want to keep some of that around. So in this case, it might be more the opposite, like 0.8 times your input plus 0.2 times your state. I want to keep a little bit of that around for future reference. And so that's what the extra weights on these earlier tokens are doing, is they're not necessarily just saying, I need to attend to this for predicting the next token as of right now, but I'm going to keep this. And then every attention layer passes this information up the residual stream. And so if I say, I think this might be important later, then I can just sort of shove it onto the residual stream for the layers above me to say, thank you, because I actually needed that information about that token that came a while back. So if this is like, I mean, I don't know if it can really get that smart, but if you know that this is the introductory sentence to a chapter, introductory paragraph to chapter, you might say, oh, I better stash some of these concepts because I think people are going to, want to refer to this. This is a very important main topic sentence. We should preserve this information for much longer. Whereas if it's just some random middle supporting sentence, then maybe, it's not as important. You don't need to. So that's the general gist here of having sort of these separate weights. And so it ultimately what it means is that these like query key weight matrices have double the parameters. The query has double the parameters because it has sort of the normal blue parameters and has these extra green parameters. And like I say, the desire is for the green ones to function slightly differently. Okay. There's a few more technicalities involving how do you do position embeddings with this scheme. But the main concept here is that if you just treated the green identically to the blue, all you would be doing is doubling your window size. By giving them separate weights, ideally, the transformer has the power to learn to do something different with green ones than it does with the blue ones.
Did they have an intuition about how it might treat it differently?
Well, the idea is this, and I don't know if I've got really sort of a great diagram for this, but basically, if you're doing normal attention on these 4 tokens, and you have these green ones over here before it, okay, then even though this is the very first layer of the transformer, even though your attention window is 4, you have information about 8 tokens. Okay. But this token over here, actually, when it does its thing, this token over here, when it does its thing, it knows about tokens even further to the left. So that by the time you get to the second layer, this token not only does it know about these 8 tokens, but because this token was influenced by tokens over here, right? The idea is that this second layer will be able to see maybe like 12 tokens, or I don't know exactly what the right receptive field is, but and then this one might be able to see 16 tokens. I don't know if it like doubles or what, but the idea is that the receptive field as you go further up is going to keep getting wider and wider. And maybe that's good enough because you imagine the early layers are maybe doing some very simple grammar things.
Right.
And if you're doing very simple grammar things, you probably don't need to look back a million tokens.
Yeah.
Like just being able to look back a few sentences is enough. And so in the real world, it's not 4. In the real world, this window is going to be, a couple thousand. So that should be multiple sentences. It should have everything you really need. If you have like an it or a he and that kind of stuff, it should pretty much always have the antecedent for what to refer to. But later on, as you get, bigger and bigger into things and you're talking about some concept, the Great Depression was defined 3 chapters ago. Well, now these higher levels, hopefully they'll have sort of a bigger receptive field. I think the next diagram, yeah.
It's almost kind of like what was it, WaveNet did something like that, similar, right?
I don't remember WaveNet what it did, but so the idea is that as you go up in the layers, they're going to be able to see further and further back in time, assuming the green weights learn to do what we want. I mean, you never know what they're going to do, but the idea is that you do have the ability to treat them differently, and then you just train it, and you know, you're not telling it what to do with those weights, but it seems like that would be a useful kind of thing to do.
That does look like WaveNet. It's a dilated 1D convolution kind of thing.
Okay, awesome. So this was Transformer Excel, and then it was their hope then that if your LLM has enough layers, it has 24, 48 layers, right? By the time you get to that top layer, it's got a pretty big receptive field. But I think in the end, just like RNNs, you know, can't really decide what information to keep and what information to throw away. You know, even like an LSTM, by the time you get to like 100 steps, that's usually like pushing the limits of it. So in that same regard, I think Transformer Excel, it's a nice idea, but the problem is knowing what to keep, right? How do you really know that this is the topic sentence of the first paragraph of a chapter, and that you should really like store, this is a definition, let me just really squirrel this information away for future use, right? I don't think it's that easy, especially when you're just looking at things at the token level. So that's the main reason why Transformer Excel didn't like blow everybody away with its performance. But you can see like there's a good kernel of an idea here, and so that's why it got reused in this paper. All right, so in Infini-attention, they say, well, Transformer Excel process two actual input segments, the blue and the green, and here, instead of having the green segment be an actual segment, I'm going to replace it with a memory. Okay, and this is where we're going to have to talk about how this memory works. Okay, now the memory might be able to be a lot smarter than an RNN. The memory, if I'm really lucky, if I say my query is Abraham Lincoln, then the memory is going to say, ah, well, here's the really important things you might want to attend to in the past, you know, the Civil War and his wife and his son, you know, all those things. Okay, so now instead of having to propagate the token information through the layers like an RNN and trying to decide what potentially is useful information to keep around, the memory can just immediately recall any key that it's ever seen. So there's none of this propagating stuff. Now, if this were truly an infinite memory, then you wouldn't even have to worry about it being smart. You just stuff every token you've ever seen, okay? But the reality is there's no free lunch there, and so you do have to impart some type of smarts into this memory. You can't just shove as much as you want into it. But I hope that makes sense in terms of like how this might beat Transformer Excel, is that it's not acting like an RNN. It's more, it's a little bit more attention like, in that, right? In attention, you have direct access to the previous tokens instead of having to store them in state. And here, you sort of have direct access, but you have direct access via like memory access, not direct access. But it's closer to direct access. The real issue, though, is the memory has to work well.
I like this idea, though, that kind of the embedding that you're using, or at least the matrices, weight matrices you're using to generate the next token, is kind of different than the weight matrices that are kind of storing some sort of context or information.
Yeah. And so what we'll see is that here now you have a very dedicated unit. We were saying Transformer Excel, you hope the green weights learn that you want it to pass information. Now you just are coding up a memory module, which is guaranteed to remember things because that's what it does. Okay. So then the question is, how do you store information into a two-dimensional array, a matrix of numbers? Okay. So what we're going to do is we're going to access things by rows and columns. And so we're going to start with a matrix. We'll call our memory matrix M. And its dimensions d key by d value. And it's all zeros. Okay. Now, traditionally in transformers, d key and d value are the same. Okay. They don't have to be, but traditionally they are. And so if you have a residual stream that's 8,000 and you have 16 headed attention, then d key and d value both are going to be 512. Okay, but this will work mathematically for any size, doesn't matter. So now imagine that you have a row vector k for your key and a row vector v for your value. If you do the outer product KTV, you're going to get a rank 1 matrix, and it's going to be this shape, d key by d value. Okay, so if you do an inner product and they're the same, then you get a scalar. That's the dot product, right? But we're not doing an inner product. We're doing an outer product, which is going to give us a rank 1 matrix. All right. So what happens if you take this matrix M and you multiply it by your query? And for now, let's just assume that the query is identical to the key that you use. So I stored it with cat, and now I'm coming up with query, and I'm coming up with cat. These are numbers, but it's cat. It's the exact same thing. So if I left multiply this, if I do q times m, so q times m equals q times, and then this is KTV, right? So it's q KT v. Because matrix multiplication, vector multiplication is associative, I can rewrite the parentheses. And this is the same thing as QKT V, which is basically our transformer attention equation. Okay, so if QKT, the dot product of these two, equals 1, then it'll be 1 times V, and I get 100% perfect recall of the value that I stored in this matrix. So if you have a memory that's initialized with all zeros, and you store 1 key in it, and you try and pull it out by the exact value that you stored it with, you will get a perfect reconstruction of what you stored. What happens if you store 2 things in there? Well, if you store 2 things and the keys are orthogonal, then you'll be able to get perfect recall on both of those keys. If they're not, then you're going to get potentially some interference between them. Well, in high dimensional spaces, all vectors are virtually orthogonal even when they're not orthogonal. So what that means is your interference between different keys is going to be relatively low. Now, the other thing that works really well about this concept is, what if you stored, again, let's just start with the simple case where it's the very first value, okay? We have all zeros, and we put in a key, and it's the key for the word great, and it's got certain floating point numbers. And then we try to pull a value out of it, but it's for the word excellent. And it's similar, but it's not the exact same thing. Then basically what's going to happen is this QKT dot product over here might be 0.9. So you'll get like 0.9 of your value out. You won't get perfect recall of the value that was stored with great, but you'll get 0.9 of it, which is, probably pretty darn good. And maybe it's even appropriate because it actually isn't the word great. It's the word excellent, and excellent might mean something slightly different. So you don't want 100%. And so this is the way in which this is sort of an associative memory that allows you to pull things out and you can pull them out fairly exactly if you have an exact match, but you can also do this kind of fuzzy matching, just like attention does, where you know, when you do attention on the previous 8,000 tokens, you don't just get one token. It's not a one-hot thing where you just get that. You get it a weighted average based on the attention scores. And so even when we say strong attention, maybe we're talking about 0.8. And so you're still getting 20% of a little, like, you know, blending of all the other tokens along with the one that you're truly attending on. And so the same thing's going to happen here, where a lot of times QK is not going to be 0.999. And so you're going to get maybe 0.8 of one of the keys matching. And the other stuff will also match a little bit. And so you'll end up getting sort of this blending of different keys that were stored in this memory. And this all works with just plain old simple matrix multiplication. So every time you want to store something in there, you do the outer product to the query with the value. Every time you want to do a read, you left multiply this two-dimensional matrix. It's not a super high-dimensional tensor. It's just 2D, just like in your math books. You left multiply by query, and you will get out something that is d-value long, but it'll be sort of this blend of different things that were stored in that memory. If the query and the key really, really don't match, then this dot product will be very close to 0, and you're not really going to get anything out for that particular key that was stored in there. So until your memory is full, you can imagine that this thing's going to work really well, that anything you store that you don't want, so something was stored for the word salty, you're not going to pull that out when the word excellent comes along. But the thing from the word great that was stored in there, that is going to come out pretty strongly. And if you had multiple things, you had great and wonderful and superb, then maybe what you're going to get is some sort of rough, you know, average of those three things, because they're all going to match a little bit, and then they'll sort of all get pulled out when you do this matrix multiply recall. All right, let me pause here halfway through the slide. Does that make sense in terms of how to use a matrix as just sort of a memory device?
So Ted, when you're adding to M,
yeah,
do you do anything to the existing values of M? In other words, like what was it that we saw in diffusion, where you adding noise, just you got larger and larger variance. The way you had a controlled variance was you would add noise and also decrease the existing. Is there anything like that where you decrease the existing M?
Yeah, I think there was a
Okay.
a normalization. I don't remember, but yeah,
So it kind of builds in a forget, is basically what it would be doing.
Yeah, it's not explained well, but there are these sigmas, and I believe their function is to basically take your result and give you something that's like norm 1.
Yeah. Okay.
So that your vector doesn't explode, your variance doesn't explode as you
Right.
store more things in there.
Okay.
Yeah, that's a great question. All right, so let me get to the second half. So basically, storing into this memory, what you do is you just do the outer product and you add it to the existing matrix. And then, yes, theoretically, something bad's going to happen if you try and store too many things that are too similar. And ultimately, even if you store things that are orthogonal, you're going to run out at some point. And so then at some point, you're going to be munging this memory as you still put more and more things into it. Okay. Like I said, so writing is just adding this outer product. Reading, you multiply and you'll get something. There's some extra details in the paper. So they use this sigma to normalize Q and K. When you actually perform this, during training, you can actually do this just like transformers do all the token positions at once using a big giant tensor multiply. You can do the same thing here. You can do all of them at once. And there's this delta method, which I forget what paper it comes from, but basically the short version of it is, what happens if I've stored great in here and now I want to store great again because this token came along? Or what if I want to store excellent or whatever? And so what they do as a slight modification to the algorithm is you don't just do the outer product of K and V stored in there. What they do is they check to see how strongly this key matches in the first place. And then they do something like 1 minus that as the weighting for what they add in there. So if it comes back as like, holy cow, you already have a 0.98 match on this key, then they will still add something in, but they'll downweight it they'll multiply it by 0.02 in order to just say, I'm only going to add a little bit because I've already put this one. So if you get text that just has the same word over and over and over and over again, it can actually really distort your memory because you're just writing this one word hundreds of times. And this sort of guarantees the diversity of what you write into the matrix M, because by the time you've written something a few times, it's going to be like a 0.99 when you try and read it out. And that means that you're basically not really adding it in anymore. And so it's a sort of a soft version of saying you only get to write each word once. Kind of like that. Now, again, once you get to the higher layers, even the same exact token isn't going to have the exact same key vector because it's context dependent. Okay. So this is not a hard and fast rule. This is just a more soft rule in terms of, but the general gist of it is the principle of you kind of only get to write each thing once. So once again, Transformer XL had 2 actual input segments. We're not going to use that green segment. What we're going to use is this memory mechanism that we just spent some time looking at. And so the way you process things is you run regular QKV attention on the current segment, the blue part of that earlier diagram. We retrieve old memory contents by using our query and left multiplying it against that matrix, that memory. And this performs effectively like a linear attention where we just get back, again, some weighting of previous keys. What they did in this Infini-attention is they did not have separate weights. They did not have the blue weights and the green weights. What they said is every layer and every attention head learns a weighting parameter beta, which is just basically at 0, I'm gonna, so you have like beta and 1 minus beta as the coefficients in front of the thing coming from the memory and the thing coming from your regular attention. Okay, and I don't even remember which way it was, 1 or 0, but I'm just gonna say for 1, use the regular attention and throw away the memory. At 0, use the memory and throw away the attention. And at 0.5, then you're going to use each equally, and you're going to literally sum them together. You're going to blend them together. Okay, so this saves them having to double the number of weights for the queries. So they add those two together, and then this output is what comes out of the attention layer and continues on for the rest of the transformer. But then also you are going to perform a memory update because right at the beginning you do a read to calculate your attention, but then you're also going to store the current token in there, and it's going to use this special delta rule. And so once you've then done this memory write, now this memory has been updated with your most current token. It's cumulatively updated, and it's ready to be used with the next token. Does that make sense? Just in terms of how Infini-attention does its processing. So if you have 16-way attention, it's possible that 10 of the attention heads are really just have beta parameters that they're really just focused on normal attention, you know? And it's possible that 4 of the attention heads have beta parameters all the way the other end, where all they're doing is just grabbing stuff out of memory. And then maybe 2 of them are kind of in the middle where they're actually kind of blending the two. Because in theory, a regular full attention would attend over the current window and the history. They're not 2 separate things, right? It would just be one thing. So if you know kind of how much, if you say 80% of the, let's use smaller numbers, 60% of the time it's in my current window and 40% of the time it's older, then if you do like a 60-40 blend, maybe that somewhat simulates that. I think I have another comment on that coming on another slide.
So Ted, is it reasonable to think of this as, rather than having double the number of weight matrices for the green or the yellow, instead you just partition it by the attention heads and let it figure out what fraction of the key should be going towards memory or to normal
That's
attention?
the general gist. So you would think that Transformer XL, it has twice the number of parameters for the queries, right? Here, you would think maybe it works better if you have slightly more heads, you know?
Right. Right. But it allows it to have different fraction using the memory at different layers.
Exactly. So the early layers, maybe it says I'm mostly only going to do blue. I'm going to do regular attention
Right.
because I normally don't need that much context. I'm just
Right.
trying to figure out, is this a noun? Is this a verb? Is it plural? You know, like it doesn't need a whole lot of context for that. But higher up, you might think it might need more weight on being able to do memory recall. And then the other thing is that it's not like you're taking a regular transformer and you're just slamming this memory in there. They're both being trained from scratch. Right. And so they know what the other's doing as they're learning, right?
And the beta is, for each attention head, is a learned parameter?
It's a learned parameter per layer, per head. Everyone gets to learn their own beta.
And then that beta applies to, once it's learned, it applies to all tokens, basically.
Yeah. Yeah.
Okay. Cool.
So here's the diagram from the paper. I think it's good to have a visual, but this diagram is not the clearest, and then I think they got their subscripts wrong in the caption. But the basic idea is, imagine that you've got a window size, it's 8,000, but you're already on the 50th thousand tokens. So there's 42,000 tokens that are not in your current window. I'm going to do regular attention on these 8,000 tokens. And then I'm going to use my query to say, hey, is there anything important from the previous 42,000? Or actually, not is there anything, but what will you retrieve from the previous 42,000 tokens? And based on the beta parameter, my head is either going to pay attention to the green or pay attention to the blue or blend them together. It's going to decide what to do.
Can you go over the update one? I didn't quite catch that. What's the notation for the update?
So the update is just memory equals memory plus my outer product. That's the vanilla update.
Okay, and what's the notation, the S-1 and S then?
They're just saying this is the latest window, and this is what in Transformer XL would have been called the S-1 window, but it's not. Well, actually, it is a window. So this is the same width as this. So if this is 8,000, this is 8,000. So you're actually doing 8,000 memory recalls on the green, and you're doing 8,000 direct, regular, normal attentions in the blue. And then based on beta, you sum them, you weighted sum of these. But again, you can always think of it, this is one thing that was not clear to me in the paper, is exactly how does this window business work during training. During inference, I think it's much more straightforward because at inference time, you're always at the last token position, right? So at inference time, it's pretty easy to say you're going to have your most recent 8,000 tokens, and you're going to have 8,000 memory recalls that corresponds to these 8,000 keys. I'm sorry, these 8,000 queries. And you do this weighted sum, and then you percolate up to the next layer. But yeah, it's not super clear in the paper exactly how much, but that's the concept. So basically, if something really important is 9,000 tokens ago, that's suboptimal because it has to come from the green. If stuff is in the most recent 8,000, you would like that to be as high a percentage as possible, because then you're just doing normal attention. You just don't really need anything for that.
So, and sorry if I'm just stumbling on this, but so these key values are being pushed into the compressive memory. Is it after the window that they get pushed in? So that did you say that they're like 9,000 tokens ago that they got pushed into?
So at inference, basically what happens is we are now at the 50,000 token, okay? And we're going to do this operation, and even if I'm waving my hands a little bit and not explaining exactly how you do this, okay? But we're going to do, 8,000 true attention queries here.
Yeah.
8,000 fake ones. We're going to sum them. But then when we're done, we're going to say, I've calculated something for the 50,000th token. I now need to write that to memory. And then we're going to repeat this for the 50,001 token.
Oh, okay, so
we're
it's
going
the
to
current.
repeat that for the 50,002. But every token that I see, I at some point have to put it in the memory, or else it won't be there for the next token that I process.
Right. So in the Transformer XL, I thought it didn't get into the green until it had passed the window for the blue.
That's right. There's a slide coming up on this. The memory does not need it. It's instantaneous. After each token, it's in the memory and it's recallable right away.
Okay.
Yeah, in fact, that might be the very next slide. Nope, it's not. But it's coming. So yeah, so anyway, so the idea, this is the idea that again, instead of waiting for things to percolate up through the layers, you just do a memory sort of. So the one tricky thing about this is that the attention weights in the blue always sum to 1. And the attention weights in the green, I don't know if they always sum to 1, but you can think of them as summing to 1, whatever. So there is no smart mechanism to decide how to blend those. Beta is a trained parameter, it's hard-coded. Right? You don't get to make a context-based decision how much to use the blue, how much to use the green. It's hard-coded at inference time. It's 0.7 times the blue plus 0.3 times the green. So that's the part that it's not clear to me how the model decides to blend the two informations. Right?
And the beta is for the read side, is that correct? It's the query side, not the update side.
Correct.
Okay.
Yeah.
And there's not a equivalent parameter for the update side.
Nope. The update is just doing a full update, a store operation. Although there is, again, that delta rule that says if you're already in memory, then don't keep pounding it over and over again. So it seems to me that perhaps this model needs to sort of let the next layer decide between the green thing and the blue thing. Because I don't really have any computing horsepower to decide between them. I'm just gonna blend them,
Mhm.
Whatever my beta tells me, I'm going to blend them 80-20, 70-30, 10-90, you know, I'm just going to blend them. But you could imagine that if you have information that's sort of like orthogonal, whatever, then you could pass it on up, and the future layers would know, even though it's already been blended, it would know, I can see this part came from the green and that part came from the blue. Right? I still have 512 dimensions. I can stuff stuff in there in different directions.
Do you kind of have a little bit of control in the sense that the beta is a per head thing, right? And so the query matrix can decide whether for that head you should, which head should access memory.
Yeah.
And so it kind of can prioritize.
Right. But I think then you're still sort of saying, now that I've said I'm going to specialize on the green memory, and this other head is going to specialize on the most recent 8,000 tokens,
Right.
You're still kind of saying, hey, next layer, we've specialized, but you got to decide what to do with what we came up with.
Right. Although the query matrix can decide what to pull out of the residual stream to use to access either near the memory or the attention.
Yeah. There's sort of this similar problem in just vanilla attention. And so this is the attention sinks, which I can't remember. I've talked about it, but I can't remember if we talked about it.
I just watched that
one. But
you
can't not attend to things.
Yeah.
The softmax has to add up to 1. So there's sort of a similar problem here that you can't sort of say, oh, on the word ball, I'm going to decide not to pay attention to the green stuff because I don't really need it. But when I get to the word red, I really want to pay attention to the green because I feel like I need it. No, you can't do that. It's pretty hardwired. But that's where I'm saying the layer above you could actually decide to do it.
Mm-hmm.
Have you read the Mamba 2 paper? In the Mamba 2 paper, they're not using the softmax anymore, and they say it solves the problem of attention sinks. And I think somebody else before them also did that. I don't remember the citation. I thought that was very interesting.
I have not read the paper yet. I did see, though, that it's like 40 pages.
Yeah, it's great. Gives us more to chew on.
The attention sinks paper did say that, hey, here's a different function you could use instead of softmax. Doesn't always have to add up to 1. Personally, throwing 1 token, I mean, if Google now allows you to have a 2 million length tokens string, dedicating 1 token for the sync doesn't really seem like it's too costly. So I don't know. If it works better than softmax, great, but it seems to me like just throwing away 1 token out of 2 million is not really too much of a price to pay. All right. So let's look at time. Let's keep going here. Okay. So so Transformer XL, again, I've written this, I've copied this bullet like 3 times now, right? It processed 2 actual input segments. We're not going to have this previous segment. We're going to use our memory mechanism. So here's 2 key improvements. The memory directly stores values. Okay, so this is not like an RNN where you have to kind of like decide what to keep and pass it on down and hope the state makes it and whatever. No, it's a freaking memory. If you store it, you can actually store it with fairly high fidelity. Okay. And then the other effect, which we'll see on the next slide, is that every layer, even the first layer, has access all the way back to the first token. Okay, you don't need to wait till higher layers for the receptive field to grow. This memory just flat out, when you're on the millionth token in the first layer, yes, you can only do attention on the most recent 8,000, but the previous 992,000, assuming your memory hasn't gone past capacity, you can just, if you wanted to, you can just pull out a word from the very first token. So the idea here is if you pick a reasonably big segment size, okay, I've been saying 8,000, you probably want something a little bigger than that if you can afford the compute. The bigger you pick, the more the compute. But if you pick reasonably big, then attention's going to work normally most of the time. For just stuff like when you say he or it, you're referring to something that came within the last like 50 tokens, not even like 8,000, right? And then if your memory works really well, and this is probably the biggest if, then yeah, it's wonderful. You're going to tend to any token no matter how far away. This is the big if, is how well does this memory actually work? So let's look at this diagram. This is from the paper. If this diagram works for you, great. If it doesn't, don't worry about. In the Transformer XL, this gray sort of represents the idea that the further up in the layers you go, the farther back you can see. Information sort of propagates further back for higher layers. And then you'll notice the gray is not the staircase. It just goes all the way back to the very beginning, because segment 3 can see even the earliest token from segment 1, even in the very first layer, because what's happening is segment 3 is accessing the memory, and the memory just has all prior information. To the extent that the memory is working, it has all prior information instantaneously available. So here's one thing that we've kind of talked about. So let's go through this. The authors state that many attention heads specialize in either local attention, the blue stuff, or just memory attention, the green stuff. And then there are a few that act as mixer heads. Now, when you look at these numbers, I'm not really sure that this assertion is highly accurate. I see a lot of values that are close to 0, 0 and 0.1. I don't see quite as many that are 0.9, 1, whatever. So, I don't know. Make your own decision whether or not you really think that attention heads specialize. There's also not a super obvious pattern from this diagram that the early layers mostly do blue regular attention and the later layers do more green. It seems kind of more evenly split. Results for time, I'll go through fairly quickly. So they trained this, and if you use really long text, then the Infini-attention had better perplexity than other non-full attention models. There's no real comparison, because when you get to really long text, there are no models that actually support, 500,000 tokens just using full attention. Perplexity is not really a super great way to measure the quality of your model. So this is a good sign, but it's not a super compelling result. They did this passkey task, which if you guys don't aren't familiar with it, it's like this super long text is going to say dog, apple, banana, rose, red, purple, dog, apple, banana, rose, red, purple, dog, apple, banana, rose, red, purple, dog, apple, banana, rose, red, purple. The secret passcode is 1, 2, 3, 4, 5, 6. Remember this code, 1, 2, 3, 4, 5, 6. Dog, apple, banana, whatever I said, rose, purple, dog, apple, whatever. So it's just going to be buried in the middle of a bunch of garbage throwaway text. And then when you get to the very end, it says, hey, what's the passcode? And it's supposed to spit out 1, 2, 3, 5, 6. And so the trick is when you do this, sometimes the passcode has to be early, sometimes in the middle, sometimes late, so the model can't cheat. And so the only way it can actually succeed at this task is it truly has to be able to remember and to be able to attend to everything. And so you can see with these sort of like hundreds scores here that when the model was fine-tuned for this task, it was able to do quite well. Somebody else I was talking to about this commented that it might be a little bit easier for it to solve the task because you keep repeating, dog, apple, banana, rose, purple. And so it might not learn to attend to the passkey. It might just learn to ignore dog and ignore apple and ignore banana. Yeah, I think that's an interesting point. But they did not create this passkey benchmark. This is pre-existing. So despite the fact that it may be slightly gameable, you can see that that other models and their model, when they don't fine tune it, actually still stink at this task. So then they did book summarization. They gave it 500,000 tokens from the beginning of, you know, whatever, War and Peace, and that sort of a thing. And they said, summarize this. Rouge is not a great metric, but it's kind of all we have today for summarization. And so you can see here some of these other models, and they did beat it. So I don't know a ton about summarization benchmarks, and there's probably not that many comparisons for 500,000 token length text. There's this other phenomenon that they tested with their summarization. They said, hey, what if I only give my model like 16,000 tokens? What kind of Rouge score does it get? What if I give it 32? And so the idea is that as they gave the model more and more text, the Rouge scores went up. So that's a good sign that it's not just that something about this model was trained better. Like what if they used a slightly different activation function? What if they used a slightly different training schedule, learning rate? You know what I mean? Like, and it's just like a really good summarizer. It's like, no, actually, when you don't give it 500,000 tokens, it doesn't know enough. It doesn't summarize well. It only summarizes at 19 when you give it a lot of text. So this is not solid proof, but it is, again, more evidence, more credible evidence that they didn't just build a model that happens to be good at summarization. They built a model that seems to use the text if you give it a really lot of it. That's a sign. All right, so to kind of like wrap up the coverage of this, so you start with Transformer XL, and you've got segment 1, and it's the green stuff, and it's going to propagate as you go up the layers, further and further and further. This linear attention transformer had nice linear scaling, but it didn't really work that well. Imagine an RNN where you're doing one token at a time. So I feel like to a certain extent, this memory thing breaks you out of that, and it also lets you sort of take some of the RNN properties and soften them. So like imagine if you could build a really smart RNN that would take 8,000 tokens at a time. Even if it failed after 100 sequence length, it's still going to be 100 times 8,000 instead of 100 times 1 token, right? So just this general idea of if you chunk things up and you still have some wall that you're going to hit, at least you're going to hit it a lot later. And so once again, the Infini-attention is going to pack much more information into what was the previous segment for Transformer XL, because the previous segment of Transformer XL is literally this previous segment and this idea of like an RNN, I've said, passing stuff up through the layers. Now you've just got a memory unit. So nobody's saying this memory unit is perfect, but you can imagine it's just a lot more straightforward for the memory unit to do recall. And there's this nice clever trick that normally when we talk about a memory, you use a key to store it, and then you try and come back to pull it out with the same key. But in this case, we're pulling it out with queries, which means that it's inherently doing a query key similarity in order to do recall from the memory. And so it's like you get this free query key similarity functionality just simply by virtue of trying to recall from the memory. And then in terms of the scaling properties, that's what they're talking about. The memory is constant regardless of sequence length officially. For longer sequence lengths, you might need a bigger memory. Okay. And then the compute is linear with respect to the sequence length because I've been saying 8,000. You always pay the cost of quadratic attention on the most recent 8,000 tokens, and one memory access is the same cost. It's the query times this matrix, regardless of whether you're currently on the 5,000th token or you're currently on the 5 billionth token. It's still going to be the same cost. So nobody is saying in these numbers that the quality of the language model is going to be just as good, but the compute and memory costs are linearly scaling. That part is indisputable. So that's kind of the overview of this paper. I do have references to these other papers. So this is Transformer XL. Munkdalai was not the primary author, but he's one of the authors on this associative fast weight memory paper. And then this is the linear attention paper from 2020. I think that's it. And then there's this other reference, Transformer FAM, feedback attention, another interesting paper. So we're mostly out of time, but if we want, we can take a few questions, or if there's anything, any of the details from the paper itself, we could actually go through some of those. So I'm curious if you guys are thinking, if you understand, or if you're lost.
I'm still thinking about the memory updates and how those are working. When you have multiple attention heads, they're all sharing the same memory, are they? And what you're putting in was the full residual stream value is what you're adding to it.
You know, I don't think the paper actually says, okay, you would think logically you're going to have a separate memory for every layer, right?
Yeah, okay. At least for every layer.
And the way regular multi-headed attention works, you don't share queries and keys across heads.
Right.
Okay. Each has their own separate W sub Q embedding matrix. So if you have a separate W sub Q embedding matrix, it seems to me you would just want a separate memory. Okay. Now, given the fact that in high dimensional spaces, most things are nearly orthogonal, you probably could get away with, instead of having 16 separate memories for each 16 heads, just have a memory that's 16 times bigger and make your life a little simpler.
Right.
But I don't know.
I can imagine here that if you had something that we didn't really show it in the diagram, but there was some decay, some normalization mechanism for the memory, so that the memory doesn't grow. It's what would it be, the diagonal matrix? The magnitude doesn't grow. I could imagine it being such that you could have different heads with like different decays on that. That kind of how long do you remember something? Could be different for each head.
Yeah, that's an interesting wrinkle. I think that what they were going for, they were hoping that the memory would remember forever.
Which it can't. It can't remember everything forever. And right now it doesn't sound like they have a selective what to put into it.
It can't, I mean, obviously it can't literally remember forever, but you could imagine hypothetically that if you didn't, this memory works as you see tokens, stuff gets shoved in.
Yeah.
Okay. But imagine that you ran a giant corpus of text through a particular language model and you got what all the queries and keys looked like. Okay, so you had this data set lying around. You could build a memory pre-computed that sort of has like the average representation across all possible queries and keys. Sorry, it's not all possible, but all possible from your data set.
Yeah.
Right? And so you can imagine that if you expect similar queries to have similar keys to have similar values, then you could just model that space, right? So in other words, if you can interpolate the value out by interpolating between what was stored for cat and what was stored for dog, then this memory might have a very soft degradation pattern when it's overfull.
Yeah.
If you cannot interpolate, if the value for cat and the value for dog are as different as the value between cat and the value for purple, then you're screwed. When your memory overflows, you're really just getting, problems.
Yeah.
So I don't know. I don't remember if they said it, but I got the vibe that they were thinking that it was going to act more like the first case I said, that similar things will have similar values and you can cheat a little even when you're not able to fit everything literally.
Yeah. No, that makes sense to me, that kind of that soft compression, I guess, is what you're thinking of. But I think if you look at like Mamba got, if I remember correctly, Mamba got a lot better when they added kind of this selective update mechanism, right? It could decide when to write a lot into the stream, into the state. And that same type of thing where you could keep your memory, you could choose what are the important things to add into it and what's just adding noise. It seems like it'd be a lot more valuable. And then if you had different memory chunks had different time domains, how long do they forget? How long do they remember things? I don't know, it just seems like it'd be an interesting combination that uses that memory more effectively.
That's an interesting concept. I don't know. I haven't read the Mamba 2 paper yet. I don't know how much of that might be echoed there.
Julius, have you been through the Mamba 2 you said?
I'm about a third of the way through it. I got to the part where they were saying no softmax. But even the original Mamba had that. I mean, the idea of selective input, input gating was a big step forward. That was a big step. So I think that does sound like a good thing to try. Make the update learned as a function of the input. Have just some sort of input derived gating that decide, like the word how often do you really need? Stuff like that.
Yeah, I mean the difference there is that Mamba really is like an old-fashioned RNN and it's processing things one at a time. So like your decisions just have to be so correct every time, in theory, if you did something like these guys where you said, I'm going to have a window and I'm just going to do full attention on the most recent 8,000 tokens, and then I'm going to let Mamba handle anything older than that. That might be a way to say, I'm going to get the 90% benefit of transformers when it just needs to hit the most recent stuff. And then I'm going to use some version of an RNN or a memory for the older stuff,
that might be a good segue into future papers. The Jamba does, I think, a little bit of that, where they kind of mix attention layers with Mamba style layers.
Yeah, I don't remember. I think it might be more of just an actual like alternating, and so
yeah, right. Although given that there's a residual stream that you're adding to, kind of it's whether they're stacked or parallel kind of doesn't matter as much.
Yep. Yeah, but in theory, those, I mean, it's all worth considering. But I feel like, well, even if every other layer is full attention, you know,
Yeah,
million,
right.
2
We still
million,
have a
that's
problem.
still going to be way expensive.
But the difference here is that these guys are saying we'll use a sliding window for attention layers, right? And they're going to be using some sort of exponential decay on a memory module in parallel with that. So you could think of the same thing as you know, a Jamba might be doing a sliding window for a full attention, and then you know residual stream or
Yeah.
kind of a Mamba stream, state stream that lasts a
Yeah.
long time.
Yeah, if they didn't do full attention, I don't remember. I have to go
Yeah,
back and look.
I don't know
But
either.
yeah, so but but all of these you can see like the gears turning, like how can we have something that's much cheaper, but that will remember stuff from long ago, right?
Right.
And you just cannot do it with a vanilla RNN LSTM, because you just need much smarter logic to decide, and that's where Mamba, you know, comes in with its different dynamics, so that hopefully maybe it will.
Yeah.
And then you can see this one, they just didn't even try to build some type of state transition, formal state transition logic. They just said, you're going to keep piling onto this memory, and it will have its own transition as you keep piling things
Yeah.
once it gets kind of full. But it's the same, trying to draw from that same book of how do we get the right keys out, keys and
Yep.
values,
Yeah.
without literally having to store all of them.
The memory looks a lot like a associative memory paper that we did probably 3 years ago or so. That same type of kind of you
Yeah.
update everything at once.
Yeah, and I think people have known about like using a matrix as like a memory, but
Yeah.
it's this sort of clever juxtaposition of you do your writes with keys and you do your reads with queries, and that does an automatic similarity
Mhm.
for you. That I thought that was like, oh, and so rather than having an expensive computation, it's sort of baked into it.
Yeah. Yeah.
And didn't you say that if the vector's already in the memory, then it doesn't pile it up? It like first looks at how much of it's there already, and then make sure it doesn't, you know, pile it
Yeah.
up forever.
Yeah,
So really, then this.
if you look in the paper, they call it this delta rule.
Mhm.
Okay. And basically, where is it? But you see, there's this V and then it's this minus. Okay. And so
Mhm.
basically, what it's saying is I'm going to scale down the value based on how much I already successfully pulled it out of the memory. So if I could successfully pull it out of the memory 98%, then I'm going to crank down this V an awful lot. But if this comes back 0, that I can't, that my V is not already in the memory, then basically I'm just using V unaltered. So this
Yeah,
is
that's
just the
great. So
ratio of how much is it already present in the memory.
so if that's normalized right, then you can really just think of it as a sum of all unique inputs, right? So
Right.
Right.
it's the sum
Yeah.
of all inputs minus duplicates.
Right. So then the only problem is, what do you do when you have more uniques than you have memory capacity? And that's where you hope that this interpolation, this similarity, allows you to actually compress more keys than you actually have physical spots. If they live in sort of vector space, then that would be perfect. But we don't know if they do or not.
You know, the other thing, Ted, you said that is an interesting idea is if this memory can be kind of become the summary of that book that you just parsed. Being able to have reference to that kind of in a RAG style, you'd be able to just load up this as a parallel block, right? To just access multiple memories, you know, throw in a couple references and
Yep. Yeah, now it's more complicated than what I'm saying because again, what we talked about, even the word great becomes very context dependent as you go up the layers.
Yeah.
And so even if you have a vocabulary of 50,000, it's not like there's only 50,000 things you need to store. Once it becomes context dependent, then there's an infinite number of things you need to store. But still, I can see. I don't have a strong opinion, but I could see that they might be right that that you can somewhat interpolate between different keys.
Yeah.
But if somehow you had a key here and a key here, and your new key is halfway in between, then the value that you want might actually be similar to halfway between those values.
Yeah.
Might
What
not
about
be
positional
true.
encoding?
What's that?
I don't see any positional encoding for
Sorry,
the
I
older
left
block.
that out of the slides.
Oh, okay.
And they handle positional encoding. They
Okay, so you got some
basically
kind of
say,
rope thing going on?
I think basically what they say is, I've been using 8,000 as my number the window, 1 through 8,000, and number the green stuff 1 through 8,000, and shove it in there. That's basically the
And they
answer.
don't.
So if you're
They
pulling
don't
it out of the
rotate it.
memory and it was from 80 bajillion tokens ago, you're still numbering it 1 through 8,000.
Okay. It seems like rope would be nice to add to that. Just twist it so that you know how old it is. You know whether it's chapter 1 or chapter 2.
Yeah.
Yeah. Yeah.
Roger and I
don't
have
know.
a project.
I don't
There you
know.
go.
I don't know what. I don't know how much value there is in knowing how long ago did I talk about something. What's more important is they need sort of the transformer attention patterns to not break, because sometimes you would say like copy the token that came immediately before me. But
relative position.
If I'm token 1,000,001 and the token immediately before me is token 200,000, then it's not immediately before me anymore, based on that. So it's almost like for what you were saying, Julius, you would need to have 2 sets of position encodings. One that lets you do token arithmetic the way that's pretty darn important, especially because a lot of words require more than 1 token. So it's very common that if you have a long word, juxtaposition, that you say juxta and then you need pause to come next, and it doesn't matter whether you're at the 1,000,000th or the 5th token. You need that relative stuff, right? But you could have like a second set of token embeddings that just tells you sort of the age of the token, so that maybe you give more priority to things that are more recent if they have similar other weights. I haven't heard people talk too much about age of tokens in long context. It's usually the reverse. It's usually like, I have a textbook, and in section 4, I'm now going to reference something from chapter 1, and I'm going to reference it like it was the immediately preceding page because I'm sort of ignoring the other sections. This is a new section, you know what I mean? And so 1,000,000 tokens ago, when I said that, I want you to treat it like it was only a sentence ago. And so that's usually more the case that I hear people trying to get the transformers to do better at, versus saying like, well, that character Bob died in chapter 1. Can we stop talking about him?
Need a special history edition.
Got a hand raised.
Yeah.
Yeah, James?
Yeah. So if the number of tokens keeps on increasing, does somehow the memory diminish after a while, or because there's some accumulation going on?
Yeah. You conceptually would imagine it's going to overflow, and it can start working less well gradually, which is what the authors probably hope, or it could catastrophically start to just give you really bad answers, right? If
Yeah.
you look at the passkey thing, you'll notice that it does not get 100% answers. Where is it? As they get longer and longer, right? You can see that it gets 100% right up to 256K, but then you start seeing this 97, 96,
I see.
94.
Mhm.
So even though this is a somewhat, you could learn sort of the pattern, you could sort of learn the trick, like always ignore the word apple. It does start to degrade
Mhm. Yeah. Okay.
at 1 million tokens.
Yeah. Thanks.
Yeah, so there's two problems. There's the general problem of, can I remember at all things that came before? And then, right, we've talked about, there's the, but do I really attend to all of them equally well? And so some of these so-called long context doesn't really do well with stuff in the middle. So, you know, the original GPT-4 Turbo was what, 16K or 32K or something like that. And if you just had some really long stuff, stuff in the middle would just kind of get buried. They may also have been doing some tricks with like interpolating position embeddings and stuff. Last I heard was a while ago, but people were saying if you go up to half of what they claim is the max length, usually you get very good performance.
Hey, Ted, I didn't see any reference to what was the compute budget that went into training this. Did you notice anything to that effect? I did a quick search on the document. I didn't see it. I just
No, trying to remember even how big was. Yeah, like I said, this paper just was very sketchy in certain places on certain details. And so,
okay. I don't mean to distract us.
so here they tell you the learning rate. Yeah, no, it's a good question. But so one of the big questions is this in fact the technique used in Gemini? And we don't know yet. I don't think that this technique is going to work perfectly, because we talked about this memory, right, can get overfull. It might only work so well. So I don't think this is actually an infinite title, right? Infinite context. I don't think it's actually infinite, but it's plausible to me that if people were able to get to 1632,000 using standard-ish techniques, this could definitely bump you up by a factor of 16 or whatever, you know, like it can get you to 1 million. That seems very plausible. If the memory works reasonably well, without having to have an absolutely humongous memory, right? It seems like it could work reasonably